Hello everyone. In this lecture, we'll discuss about photochemistry or the basic aspects of the photophysics of an molecule. So we call it as photochemistry. Now, as the name suggests, this photochemistry means what is the chemistry which is induced by photon or light. And photochemistry is a very interesting process, and we'll only discuss very fundamental aspects of photochemistry, like how we define phenomenologically the different processes that are involved in photochemistry. Now, when you talk about photochemistry, I usually refer to photochemistry that happens in the ultraviolet and visible range. So we are calling photochemistry by the ultraviolet and visible light. There can be infrared photochemistry. We'll come back to it at the very end. Now, UV and visible means actually here the electronic states of the molecules are get excited, and many processes actually happen, and we'll just review those processes one by one. Now, that is the first aspect, and the second aspect is that one thing we have to you have to know is that the basic fundamental aspects of molecular quantum mechanics, like what are the energy levels of the molecule, like any molecular energy level can be partitioned as electronic, then vibrational, then rotational, and translational energy levels. Now, translational energy levels we are not going to discuss, because we are only going to discuss how the internal energy levels are populated for this discussion. Even rotational energy levels also I am not going to discuss. So what we are going to discuss is right now is that all of you know that suppose if I take if I want to represent the potential of a bond, chemical bond, in its ground electronic state, so the potential looks like something like this. So this is called an anharmonic potential, and we discussed it we'll have discussed most likely, or we'll be discussing it many times. Let me draw it a little bit more clearly. So I'll use a different color. So what I'm showing here is harmonic potential well, and on top of it I am showing the real potential felt by a molecule. Now, as you can see, at the very close to zero level in the sense close to the ground electronic level, the energy levels or the potential actually looks like, or can be approximated as a harmonic potential. So this is the harmonic oscillator potential, and this is the true potential. Which can be to a very good approximation, can be approximated by the Morse potential. So Morse potential is an analytical form of anharmonic potential, or you can actually have the harmonic potential and then you can actually expand it in terms of nonlinear terms, as we do in Taylor expansion. Now, suppose this axis is my energy axis, this vertical axis. So the energy varies according to along this axis, and this axis is nothing but the say bond length, a typical bond length. So here I have the equilibrium bond length. Now we have many energy levels. Let's approximate it as a harmonic oscillator, although at a very high energy level close to the dissociation you cannot make that approximation, but just for the sake of argument, let us think that we are approximating it to be a harmonic oscillator. Now, as you can see in the ground, this is basically the ground electronic state, and suppose this energy is 0 here, that is the 0 of energy, that is the reference 0 of energy, and then you know that the molecule should have a minimum energy which is equivalent to its 0 point vibrational energy, and each vibration, like if I kind of zoom it here, So I have a harmonic oscillator like this. Suppose this is the 0 point energy, this is the V equal to 1 energy, this is V equal to 2 energy. So this is V equal to 0, this is V equal to 1, this is V equal to 2, where V's are the vibrational quantum number, and the energy levels are, the energy expression is V plus half h bar omega, or you could write it in terms of so omega is the angular frequency, or you can write it as a circular frequency. So then actually we write it as h nu. And then each of these vibrational level will have actually many rotational manifold that we are not showing, and each rotational manifold may also have degeneracies. Actually they have degeneracies. So all these finer energy level structures we are not considering right now. And similarly, if it is confined in a suppose these molecules are in a gas phase and they are confined in a container, so then we know that for a particle in a confined box, we also have energy levels, quantized energy levels for translational motion. So these rotational levels will also further be each rotational level will have a further translational manifold, but those things we are not discussing right now. Now we will restrict ourselves with electronic energy levels with vibrational manifold. Now there is a Boltzmann distribution law, and in the Boltzmann distribution law, you know that if I calculate how many molecules are sitting at the ground electronic state and the ground vibrational state, you will find that most of the molecules are at room temperature will sit in the ground vibrational level. Now I have shown here as like I have drawn a curve like this. Now what is this curve? So this is my potential, and this is V equal to 0, and I have drawn a curve like this. Now this is nothing but the V equal to 0 wave function. So as you know that these wave functions are basically solution of the Schrodinger equation. If you use the potential in the time dependent Schrodinger equation to be just the harmonic potential, one dimensional harmonic potential, which is half k x square. If I use that, then and k, again k is basically 1 over 2 pi root k by mu. So if I write all these equations, so then you will see that this wave function will be of the form of a Gaussian wave function. So it will go as an with some constant which is the normalization constant, and then it will be something like e to the power minus ax square. So this is a Gaussian function, and to be more precise, it will be e to the power minus a x minus r equilibrium square. So r equilibrium is the center, so the Gaussian is centered around the equilibrium position, and this is basically the wave function. Now for an excited state, as you can think, excited electronic state, where will be the potential energy well will located? Now suppose this is the excited electronic energy level. So this is the zero minimum energy for the excited electronic energy level. Now the question is how the potential well will be placed with respect to the ground state potential well. Now you know that there are two interesting things that we often students often get confused. Suppose I have a molecular energy level I'm showing like this, and suppose I have energy levels. So how do you get these molecular energy levels? You solve the Schrodinger equation and you get some molecular energy levels. Now the question is this level we call it as HOMO because it's the highest occupied molecular orbital, and this level I call as LUMO, the lowest unoccupied molecular orbital. Now suppose we are exciting this molecule, meaning I am pulling one electron to this level. Now if I do that only with respect to the HOMO and LUMO, because all other energy levels will be unperturbed. So there are energy levels, these are called core energy electrons, and there are also high unoccupied energy levels that we are not writing. So we are only focusing ourselves on the HOMO and LUMO. Now the configuration will be like this. Now you have an interesting situation here, depending on the spin, because as you can see, the way I have drawn it, this is just one of the possibilities. Both spins can be up, one spin can be up, one spin can be down. In the ground state, as you see that the both spins have to be paired up because of the Pauli exclusion principle, and then I can have one up, so both can be down. Let us draw it first. So both can be up, both can be down, one can be up, one can be down, and similarly the other possibility that of the up down, it is the down up. Now electrons being fermions are indistinguishable, so you cannot distinguish which one is up and which one is down. So when you write the wave function for all of them, what you do is that suppose I call the up spins as alpha. So for this state, the total the spin, but the spin state can be represented as alpha 1 and alpha 2. So electron 1 is in alpha state, electron 2 is also in alpha state. Similarly, the down spin, if I represent as beta, so it will be beta 1, beta 2, and then this one is nothing but alpha 1, beta 2, and this one is nothing but beta 1, alpha 2. Now this is an unique configuration in the sense that if I exchange the electrons, like if I put alpha 2 and alpha 1, that is exactly equal to alpha 1 into alpha 2. So after exchange of the two electrons, so the sign of the wave function is not changing, which means actually this is a symmetric wave function. This is also symmetric, but here you cannot say whether it is a symmetric or antisymmetric, because these wave functions, electrons are indistinguishable. You cannot say that which one is up or which one is down. Now for that, actually we take a linear combination of these wave functions, and we write it in the way that if I take linear combination, I'll have two possibilities, beta 1 alpha 2, and also another possibility, alpha 1 beta 2 minus beta 1 alpha 2. Now this is the symmetric combination. Now as you can see that if I exchange 1 and 2 labeling, so it will be alpha 2 beta 1 plus beta 2 alpha 1, but that is exactly equivalent to the original configuration. However, if I change the electron 1 and 2 here, so I'll have originally the wave function is alpha 1 beta 2 minus beta 1 alpha 2, and that time it will become alpha 2 beta 1 minus beta 2 alpha 1, which is negative of the original wave function. So this is an antisymmetric combination. So these three are basically symmetric spin part, and this is basically the antisymmetric spin part, and these three symmetric spin part actually form a triplet, and that is the triplet state of the molecule, and this forms a singlet state in the molecule. However, the interesting thing here is that when the molecule was in, all electrons are paired, so this configuration has to be a singlet because all electrons are paired up. So what I am saying here right now, there is something called electronic configuration of the molecule, which I have drawn here. Like I have energy levels, and what are the electronic configuration of the molecule. It is just like the atomic configuration you have done in your high school. Like say for example, if I ask you what is the atomic configuration for lithium, so you say that 1s2, 2s1. So 2 electrons are in 1s and then one unpaired electron in 2s. So similar way, molecules also have energy levels, and we have special nomenclature for them. And if I fill in the electrons in the molecule in a similar way, from lower energy orbitals first and then the higher energy orbitals, molecular orbitals in this case, not atomic orbitals, then we'll get an energy, then we'll get an electronic configuration. Now, moment I promote an electron in the excited state, I actually have 4 different possibilities, and these 4 for the same configuration, and the configuration is 1 electron in HOMO and 1 electron in LUMO. So we call these kind of configurations together as HOMO minus, so basically HOMO has 1 electron, and in the same token like we do for atomic orbitals, so it is nothing but HOMO 1 and LUMO 1, and here it is nothing but HOMO 2 and LUMO 0. So you promoted one electron to the LUMO, but as we see that this actually corresponds to two different electronic states. So this is basically configuration. So a particular configuration that forms a state which is a singlet state. So the ground state we said is this state is a singlet state. So what we are representing here is basically state of the molecule. Now every state of the molecule also will have some energy level, in the sense that now it is a singlet electronic state, and this singlet electronic state has now vibrational manifold. Now excited electronic state means actually we promoted one electron to the HOMO and LUMO according to the electronic configuration, which is this configuration, but I can actually have 4 configurations, and these 4 configurations according to Schrodinger equation they also have the same energy because Schrodinger equation doesn't take into account of the spin energy. So they are the same kind of orbital energies, and they are also degenerate. But in reality, there is something called Hund's rule, and Hund's rule shows that the triplet will be more stable than the singlet. So we'll have basically 2 energy levels, where one will be say singlet, and one will be say the triplet energy level, and each energy level will again have some vibrational manifold. Now the question is, if you think in this way, what happened when we got the way we actually had an excited state is something like this. I have an HOMO and then I promoted one electron. So where I am promoting the electron? Now usually up to HOMO, these are actually called bonding orbitals, and the LUMO is usually the anti-bonding orbital. So once I am promoting one electron from the HOMO to the one electron to the LUMO, my bond order actually decreases, meaning I'm having one electron in the anti-bonding orbital. So the total bond order, which is defined as number of bonding electrons minus number of anti-bonding electrons divided by 2, that is a smaller number. So what is happening, if I have actually one electron in the anti-bonding orbital and my bond order is decreasing, the bond length must increase, the equilibrium bond length. There is nothing called a fixed bond length, because there is an equilibrium bond length and this is vibrating always. So that's why we have all these amplitudes of vibration, and that's why around the equilibrium position I have a harmonic potential. If I excite more, the bond will vibrate with more amplitude. However, keep in mind these wells correspond to a particular frequency, because it's a harmonic oscillator with a particular frequency. So once I'm going up and up, the frequency doesn't change. Only thing changes is the amplitude of the vibration. Now, so by that token, I'll have a singlet state. This singlet state equilibrium bond length will be actually shifted. It has to be shifted. Why? Because the singlet state actually corresponds to electronic configuration where one LUMO was promoted. So the potential well will be situated somewhere here, and it will have its own energy level, 0 point energy level, and all these excited energy level. V equal to 0, V equal to 1, V equal to 2, V equal to 3, something like that. Similarly, with the same argument, there will be a triplet state also, but usually in the triplet, you have more extension of the equilibrium bond length, and the triplet will be somewhere situated here. And these are, suppose, the triplet energy levels. Now, so this is the excited singlet, and this is the excited triplet, but it is the first triplet that we see, and this one was the singlet. Let me actually remove the dotted line, or actually we can remove the blue curve totally, and we can approximate it to be the harmonic oscillator. And this curve, which was the ground state vibrational potential, so this corresponds to a ground electronic state, which is also singlet. So usually call it as a S0 because it's the ground state. We call it as a S1 state. It is the first excited singlet state, and we call it as a T1 state because it is correspond to the triplet of the ground state. We can have triplet state also in the ground state if we have an unpaired electron. Otherwise, we cannot have an two unpaired electrons. Otherwise, we cannot have a triplet. If I have a one unpaired electron in the ground state, so then I'll have a doublet, because the spin multiplicity goes as 2s plus 1, so I'll have a doublet state there. Now let us think that I have a molecule where all electrons are paired, which actually happens with most of the chromophores. I mean, chromophore means actually it's a molecule, or it's a part of the molecule that actually absorbs light in this UV visible range. Now let us talk about a transition. Which kind of transition? Let's say electronic transition. Now what do you mean by an electronic transition? I mean how do you define an electronic transition? Now when a photon gets absorbed, a photon of say ultraviolet and visible energy, so it is absorbed, and then the molecule is promoted from the ground state to the excited electronic state. Now this process happens very quickly, in the sense that when this electronic transition happens, it happens so fast that the molecular vibrations are like kind of much slower than compared to this transition, in the sense that you can think that every bond is vibrating like this, but so the molecule was in ground electronic state, and suppose it was in a 0 point vibration, because as I said, most of the molecules will be residing at the ground vibrational level, and it is vibrating. Now when I am exciting it, during that excitation, since electronic excitations are fast, now you can think it in loosely in that way, that electron's mass is much smaller than the reduced mass of vibration of a particular bond. So you can think that just like you had this analogy of apple and earth, that when apple falls on the earth, the force acting between them is the same. So apple is attracting earth, earth is also attracting apple, but there is a huge difference in the mass, so the acceleration for the apple is more. And you see practically that the apple falls, you do not see the earth actually moving towards the apple. So it's the same analogy, and when the electrons move during an electronic transition, they are so light that their transition is extremely fast. And by that time scale, the vibration, there is no change in the vibrational coordinate. So you can think that electronic transitions in this diagram, because the x-axis is a vibrational motion coordinate, because it's a bond change in the bond length. When the transition happens, the transition will be vertical. Vertical in the sense that I'm not changing my position when I'm doing the electronic transition. So any electronic transition in this diagram, I'll show it as a vertical transition. So let me just draw a vertical arrow. So this is basically how we represent an electronic transition. If there was a change in bond length, suppose I had something like this, and I'm starting from here, and if during the transition I'm having a change in bond length, so then I can represent it like a tilted arrow, because as I'm exciting up and up, then I'm also shifting in this coordinate. But yeah, so it's not, it doesn't make sense, so we do not make this approximation here. So what we see here is electronic transitions are extremely fast, and then we also say that this is a vertical transition. So this has a name, and this principle is mostly you know what is the name of this principle. This principle is known as Frank-Condon principle. So this is known as Frank-Condon principle of electronic transition, or for electronic transition. So it says that during the electronic transition, the vibrational motion will be fixed, and on this diagram I can actually show the electronic transition, vibrational motion specifically frozen, that there is no vibrational motion during the electronic transition. Now there is an alternative description why actually this arrow, the way I have drawn it, as you can see here, the end point of the arrow is actually ending up here. So this is a very important thing. Now think about how the vibrational wave functions look like for an harmonic oscillator. So let me actually use some other color. So as I said, the ground vibrational wave function, that looks like more or less as a, not more or less, for a harmonic oscillator it will be a Gaussian. So here also it will have it will be a Gaussian. The excited vibration will actually look like something like this. because it has a node. The third one will look like something like this. So what is happening here, when I am exciting an when I am doing an electronic transition, since the upper well or the upper potential well is shifted, I cannot have the 0-0 transition to be the most predominant transition. Let me actually give you a mathematical explanation for that. So the mathematical explanation is something like this. Suppose we have electronic transition, and any transition, what we say here is that there is a transition dipole that is involved. Now what is a transition dipole? Now transition dipole we kind of discussed earlier, and as opposed to a permanent dipole, and we said that there is a kind of induced dipole which is induced by the electromagnetic field or the electric field of light, and that induced dipole causes a transition. Now remember that I can write the total wave function as a product of, say, electronic wave function times the vibrational wave function, and suppose I am doing a transition from the ground state to the first excited state. Let me actually write this name electronic and vibrational in the suffix electronic, and this is vibrational, electronic, and this is vibrational. And suppose I am going from the ground electronic state, which is corresponding to psi 1, and then I will end up in psi 2. So there is something called transition moment integral. It is nothing but a dipole operator. Again, it's a transition dipole operator that actually acts between these two wave functions. So basically it couples the ground state with the excited state. Now the ground state is so what is the ground state? Ground state is basically an wave function that has an energy this. So it has an electronic contribution as well as vibration as well as rotation and translation that we are not considering. So right now we are just writing it as a product of electronic and vibrational, and this dipole moment actually, which is vector quantity, and this mu dot E is the electric field, is actually known as a transition dipole operator, transition dipole moment, or transition moment sometimes it is called. And this is of course an operator because it is operating on the wave function. And then what we have to do, we have to basically integrate over all possible coordinate, all possible electronic coordinate. Let's say I'm calling it as a d tau electronic, and all possible vibrational coordinate. So it's basically a double integral. Now what you see here, this transition moment actually acts on the electronic transition, because we are not talking about a vibrational transition that actually falls in the infrared, because we've shown UV visible light, so it actually couples the electronic part of my wave function. So this operator acts only on the psi electronic part, this part it acts. So I can actually separate out the integral, and what I can write is that this integral is nothing but electronic coupling mediated via this mu dot E, and between the ground electronic state and the excited electronic state. So basically it's the electronic part of those two states, and then I have multiplied by a vibrational integral, but which is just an overlap integral between the ground electronic state's vibrational part and excited electronic state's vibrational part. Now ground electronic state vibrational part, how it looked like, it was basically all at V equal to 0, because ground state was always V equal to 0, because we started from V equal to 0 in the ground state. And then in the excited state, I can actually end up in some other state, but that will depend on how I am positioned in the excited state. Meaning, if my wells, vibrational wells, are exactly top of each other, something like this, then you can see, since the electronic transitions are vertical, then I have a good chance that this and this will overlap, because I have a Gaussian here, I have another Gaussian here, and then if I think mentally that I am considering the overlap integral of these two Gaussians without moving my x-axis because everything is frozen, then actually I will have a good overlap between these two wave function. Then the 0, 0 transition will be maximum. But this is not the case. Why? Because in the excited state, I already told the well has been shifted. It looks like something like this. So what will happen, I will start from v equal to 0, but I will try to end up, since it has been shifted, with some excited state wave function that has some amplitude of vibration at the corner, because if you remember that when I am exciting vertically, I am ending up in a corner, so that I will have some vibrational amplitude overlap, which is given by this Franck-Condon factor. So this is known as basically this vibrational overlap is known as a Franck-Condon factor. So the electronic transition actually, and the strength of the electronic transition will depend on two things. It will depend on this particular Franck-Condon factor, that it depends on other factors also. But right now we will be discussing only one thing, that since the electronic transitions are vertical and since the excited potential is actually shifted because of the increase in bond length in the excited electronic configuration, and this excited electronic state represents this configuration among many other states. So in order to have a maximum vibrational overlap, this will end up in some other electronic, the transition will be maximum for not for v equal to 0 in the ground state to v equal to 0 in the excited state, but it will be maximum for say v equal to 0 in the ground state to some v equal to, I do not know, the way I have drawn it as it is v equal to 2 in the excited state. So which means I will have a more Franck-Condon factor for this state than this state. So this transition will be more stronger. Now how these transitions will look like, so that we are going to draw, but before that let us actually have a quick discussion on this part. So as you can see here that we have a dipole operator here, and this dipole operator we had already discussed that it goes as x, and so it goes as just a linear term, and then we discussed that whether what are the parity rule for a dipole operator, like these two wave functions should have opposite parity, otherwise this moment will be 0. So this part, whether the parities are odd and even or even and odd, something like that, so it dictates whether the transition moment is 0 or not, but it does not talk anything about whether it is if it is actually allowed transition, how strong it will be. So that is mostly controlled by this Franck-Condon factor, and that basically talks about what is the overlap integral between the ground vibrational state and some other vibrational state in the excited manifold. Now as you can see that the spectrum will have many different features that we are going to discuss right now. So I will have an absorption spectrum corresponding to this electronic transition the way I have drawn it, and the absorption spectrum will be something like that I am going from say v equal to 0 to v equal to all the states in the excited state, and one of them will be maximum, which is not actually v equal to 0. So if I plot the absorption spectrum along this direction, so I'll have a v equal to so suppose I'm plotting the intensity versus wavelength. Wavelength usually we denote in nanometer, so the energy actually goes in this direction, so it is the inverse of energy. Now and wavelength is increasing in this direction. Now suppose this corresponds to my v equal to 0 0 transition, so we write it as 0 0. Some textbook actually write the final state in the first, so they write it like this, 0 0 transition, but the 0 0 transition will be weaker than say 0 1 transition, and that will be weaker than, suppose the way I have drawn it, that this should be written like this, it will be 1 0. So this is the strongest transition. So the vibrational spectrum will look like a structured spectrum overall. So it will have a structure like this, and as I see that in this structure we'll have basically kind of, it's a very characteristic vibrational spectrum for the molecule that we have drawn. Now you think about what will be the emissions spectrum or the fluorescence for this molecule. Now once the molecule is excited, which is a very fast process, then the population will relax, and it will relax first vibrationally, and that is known as vibrational relaxation, and this vibrational relaxation is usually fast. So within a time scale of 1 picosecond or so, all the molecules actually come to the zero vibrational level of the excited electronic state. So in the fate of the excited molecule, if we consider, first thing was basically our excitation, and that was extremely fast. If you asked what is the time scale, actually it is less than 1 femtosecond, and 1 femtosecond means actually 10 to the power minus 15 second. And then the second thing is that fine, it had an excitation, and the pattern will look like it will be according to the Frank-Condon overlap, and we said that everything is starting from v equal to 0, but some v which is not equal to 0, some higher v will have the maximum Frank-Condon overlap, and for that we have a particular structure in the vibrational electronic spectrum, which has a vibrational manifold. So this is actually electronic spectrum, this falls in the UV visible range, and then there will be a vibrational relaxation, and this vibrational relaxation is it usually competes within say 1 to 10 picosecond, and it is extremely fast. So again, 1 picosecond is 10 to the power minus 12 second. Now then it says that all the emission will start from this v equal to 0 in the excited state. Now this assumption that this vibrational relaxation will be fast than this state, say for example v equal to 2, can actually radiatively emit to the ground state, but that probability will be very low because most of the population actually quickly leaves that v equal to 2, it comes to v equal to 1, it quickly leaves v equal to 1, it comes to v equal to 0, and there it stays for a while, and from there it emits. So we call this vibrational relaxation extremely fast, and everything arising from this v equal to 0, this has a rule, and this is known as Kasha's rule. This is after Michael Kasha, who basically described this phenomena in this way, that this approximation that okay, vibrational relaxation are fast, which is a fairly good approximation. So now this v equal to 0 state starts emitting, and it can start relaxing, and then it can relax via say radiative relaxation, where actually this state emits and comes back to all the states which are in the ground state. So now you can think that there will be emission which is exactly like an absorption from v equal to 0 to 0, which means actually just like our emission, just like our absorption, the emission will also be structured, but this time I'll have a 0 to 0 emission, but then I'll have a 0 to 1 emission, I'll have a 0 to 2 emission, something like that, I have a 0 to 3 emission. Now this 0 is in the excited state, and then it is coming back to the ground state, and we'll have a similar structure in the emission spectrum also. So overall the emission spectrum will also look like something like this. It will also have a structure like this, and so we say that this absorption and emission spectrum looks like a mirror image, in the sense that 0,0 transition, as you can see here, actually overlaps very nicely, because this is practically the same energy transition, and then you have 0 to 1 for the excited state. Let me just write it like this. So these transitions both are 0, 0, absorption and emission. So this transition will be 0 in the vibrational, 1 in the vibrational state, say for example, and 0 in the excited electronic state. This is the emission spectrum or the fluorescence spectrum. Now, apart from fluorescence, the molecule will also relax via non-radiative relaxation. Now, how this non-radiative relaxation happens? This non-radiative relaxation is basically can happen due to many processes. Like if it happens in the condensed phase, it can actually exchange energy with the surrounding, and then through collision and many other processes, and then it can quickly relax the energy as a thermal energy. And among the excited state processes will have both the radiative relaxation, or basically the fluorescence, and the fluorescence lifetime, the time it takes to come back to from the excited state, is typically on the order of 1 nanosecond, whereas this non-radiative relaxation will be on the order of, say, it's a fraction of a nanosecond. It will be less than a nanosecond. Now, usually when you measure the fluorescence lifetime, you actually measure both the radiative and the non-radiative lifetime together. That is known as fluorescence lifetime. Now, what is fluorescence lifetime? Suppose I have an excited state. Let me actually draw this diagram once again. So, what I have drawn here in the preceding page, now I am trying to draw once again V equal to 0, V equal to 1, V equal to 2, V equal to 3, V equal to these were all in the excited state energy level of S1 level, V equal to 0, V equal to 1, V equal to 2, something like that. And all these levels are from S0 level, all these levels are from S1 level. And then we had vertical transition arising from V equal to say 0 to 2, 0 to 1, 0 to 0, because everything actually starts from here, and then there is a rapid relaxation to V equal to 0. So when we start the emission, we start from V equal to 0 in the excited state, and as we can see that these 0, 0 transitions are basically the same transitions. Let me actually draw this more precisely. And then we have all this energy, all this emission to the all other levels, something like this. So as you can see, these 0, 0 transitions are basically the common transition in the absorption as well as in the fluorescence. And then I have a kind of mirror image relationship. I have higher lying absorbing states, and then there is a lower lying thing. And then as you can see, there is a shift in absorption and emission. This shift, where this shift is coming from, usually you will see, this kind of nice structured spectrum you will see only in gas phase. Usually in condensed phase you do not see this kind of absorption and emission, because and particularly for two reasons. I will come to that. And you will see a structureless feature, and then you will see some absorption maximum and some emission maximum, and that difference you call this as a Stokes shift, because Gabriel Stokes first talked about this shift when he did his classic experiments on fluorescence. And this Stokes shift also, the same term also used for Raman transitions. There also we talk about difference between absorption and emission, and how much is the red shift in frequency, because you see that this is actually in wavelength scale. So we are going from the blue side to the red side. This is known as the Stokes shift. Maybe I should draw the arrow like this. And so there is a characteristic shift from the absorption in the fluorescence spectrum with respect to the absorption, and this extra energy shift means actually extra energy has gone somewhere. This has been adjusted by that vibrational relaxation and all other non-radiative processes, because everything will come back again to the ground state. and due to this vibrational relaxation, that extra energy has been can be accounted for. Now this type of diagram where actually we show the energy levels and we show it as a vertical transitions and about the singlet energy levels as well as the triplet energy levels, this is known as Jablonski diagram. But the way we have drawn it with the potential, well, it's a modified Jablonski diagram. Now, the excited molecule can actually come from the excited singlet state to the excited ground state, back to the ground state. But there can be an interesting process. This molecule or the population can also go or cross to the triplet state. I know that this is basically a spin forbidden process because I'm going from the singlet to the triplet, and this process is known as inter-system crossing because or ISC. Now this ISC happens because of spin orbit coupling, and the molecules in the excited singlet state actually due to ISC goes to the excited triplet state, and then the excited triplet state can also emit radiatively and non-radiatively. Now you can see that when it emits, we have a problem here, and the problem here is that it is actually emitting from the triplet state to the singlet state, and that emission we call it as a phosphorescence, and it has a huge long lifetime because it is coming from the triplet state to the singlet state, and which is spin forbidden, and that we call as phosphorescence. So this phosphorescence usually is long, and the typical time scales are on the order of 1 microsecond, which is 10 to the power minus 6 second, 1 microsecond. So thus we see that we can actually explain the several photophysical processes extremely phenomenologically. So I'll just give you a quick overview of what we have, or a quick summary of what we have discussed so far. So before that, I'll just quickly explain why the structures, usually if you take a fluorophore in the gas phase, you'll have a nice vibrational features in the electronic absorption, but you'll not see the same thing in condensed phase. The reason is usually textbook write that the molecules have many energy levels, and that's why you have a congested spectrum, and that's why all the lines, there will be many lines and it will be structureless, which is not very true, because if you take even a fairly large molecule in gas phase, you will see some structure. You can actually make those structures go far apart, because if you apply electric field or magnetic field, depending on the nature of those states, you can actually shift the energy levels by Stark effect or Zeeman effect, and thereby actually you can actually get a high resolution spectrum where actually the lines are for separated. And once you have these molecules, which has a structure in the gas phase, a small molecule or a large molecule, whatever it is, in a condensed phase, you have a very interesting thing. And the interesting thing is that every suppose one molecule is there, and there is one particular transition corresponds to that molecule, which has a corresponding absorption in the spectrum. Now what will happen, one molecule, suppose I'm showing this as one molecule and this as another molecule, this is another molecule. Now the local environment around this molecule will be very different than the local environment around the other molecule, meaning there are solvent molecules around, and the solvent molecules are actually dynamically changing their position, and they always interact with the molecules, and so the molecular energies are shifted or perturbed. And as a matter of fact, for one molecule you might see this energy level, for the second molecule you might see the energy level is little bit up, for the third molecule you might see that the energy level is little bit down. So these molecules, although they are identical molecules, the local environment are so different, that's why their absorption becomes a little bit broad. Now you can see I had one transition here. I had a, let me just draw it in with some other color. So suppose I had two transitions to begin with, which are very nicely resolved transitions in the gas phase. Let me draw it like this. So I have a transition like this in the, say, in the gas phase, and this transition, each of this transition, now the problem is that in the condensed phase each will be now broadened due to this different local environment of the molecules. So as a result, you will see a very structureless band for these two things, where actually you cannot distinguish these individual absorptions are now so broad that they are kind of hiding in that absorption spectrum. So the line shape actually becomes broadened, and this kind of broadening mechanism is called inhomogeneous broadening, in the sense that in your sample you have different structures of the local environment, and which is pretty much inhomogeneous, because there is no homogeneity, or there is no particular unique solvent structure around it, and that's why it's called inhomogeneous broadening, or sometimes it is called a static broadening. I cannot explain you here why it is called a static broadening as opposed to the dynamic broadening, or so-called homogeneous broadening. So those are beyond our discussion. Now let me just summarize what we have told, and we have actually talked about the electronic transitions here. And first thing first, you should remember that number one, there is an electronic configuration for molecules, just like electronic configuration of atoms, and then one electronic configuration may correspond to one or several electronic states. Like all period of configuration has a unique state, which is the singlet state. But if I have two electrons in two orbitals, I have four possibilities, because one electron in the first orbital can have up or down spin. The second one, for each of these up or down spin, can also exist in up or down spin. So I'll have 2 into 2 or 4 combinations, and those four combinations, after we do the symmetric and antisymmetric combinations, can be grouped into 3 plus 1, and those 3 we call as a singlet, which is symmetric spin combination, and the one we call it as a singlet, which is the antisymmetric combination. So I will have a singlet state and as a triplet state, but usually the triplet is lower in energy than the singlet state, the way we have drawn it. This is the excited triplet, this is the excited singlet, and this is the ground singlet. Now what happens is that when I have an electronic transition, the electronic transitions are fast, and then also the excited well is little bit shifted because of the change in bond length. So usually the vibrational overlap, or the Frank-Condon factor, will be maximum for some vibrational level of the excited electronic state other than V equal to 0. So we'll have a maxima which is slightly shifted than the 0-0 transition. And then what happens is that right after this transition, all the population actually comes back to the ground vibrational level of the excited electronic state. From there it starts emitting. Now it can radiatively or non-radiatively emit back to the ground singlet state. That will give you, the radiative emission will give you a structure in the fluorescence spectrum in the same token like we had the absorption. And then it can also go to the triplet state via a process which is a non-radiative process, which is known as intersystem crossing, which actually arises as a result of spin orbit coupling. And then from that the molecules can also emit back to the ground electronic state. But since now the ground electronic state has a singlet state, there is a spin, it is spin forbidden, so the transition lifetime will be increased, and this radiative lifetime is usually falls in the order of microseconds, that we call as phosphorescence. Now as you can see that energy wise, like I excited and then there is a vibrational relaxation, then I fluoresce, and or I can actually go to the triplet state, which is even more down, and then I do the phosphorescence. So the phosphorescence wavelengths will be even more red shifted than the fluorescence wavelength. So I'll have a phosphorescence spectrum. So this is basically the absorption spectrum, this is the fluorescence spectrum, and this is the phosphorescence spectrum. And phosphorescence is a longer lifetime component. Sometimes actually you might have the fluorescence having a longer lifetime component. Sometimes what happens actually, it comes to the V equal to 0, but it actually goes to another state which is lying nearby, because the way I have drawn it is basically few distinct states, but in reality actually there will be many different electronic states lying around. And then when I have that situation, then what will happen actually, now that population can go into some other state, and then it can come back later and emit. That will increase the fluorescence lifetime. It is called delayed fluorescence, Now then, if it is delayed fluorescence, you cannot distinguish just by measuring the lifetime whether it is coming from the singlet state, whether it's a fluorescence, or it is coming from the triplet state, whether it's a phosphorescence. Now to check that, you can actually do this experiment in a magnetic field or a static electric field, and since the singlet actually does not split into further energy levels, so its energy will not change, but every triplet will now split into 3 in the presence of magnetic or static electric field. So every line in the phosphorescence spectrum will now split into 3. So the splitting is a characteristic feature of phosphorescence spectrum, not a fluorescence spectrum. And if you have a longer lifetime emission, you can actually cross check that whether it's a fluorescence or a phosphorescence. And we talked about fluorescence lifetime, and we did not tell what exactly it corresponds to. So usually when you measure the fluorescence emission from an excited state, you will get, suppose I am talking about the intensity of fluorescence versus time, and then you will see that suppose I excite it here, and immediately after excitation you will start seeing the emission, which actually decays over time. And this you can actually fit to a multi-exponential. Suppose if I fit it with a single exponential, you will find it goes like e to the power minus t by tau. This tau is the fluorescence lifetime. So the fluorescence lifetime which I told about here, that it is about 1 nanosecond, this is nothing but the time constant of the exponential decay. Similarly, the phosphorescence lifetime is also the time constant of the exponential decay. So this is an overview again of how what are the effects of the excited molecule in terms of we explained it in terms in a Jablonski diagram, and we also talked about the Frank-Conon factor, how it arises, because the coupling here is the electronic coupling. And keep in mind that there are 2 distinct things. One is electronic state, one is electronic configuration. Do not get confused between the electronic configuration and the states. Configurations can correspond to multiple electronic states. And then we also talked about the characteristic or absorption, how the absorption and emission spectrum will look like, where the mirror image relationship comes from, and how basically the fluorescence and the phosphorescence spectrum, fluorescence absorption and the fluorescence spectrum look like the mirror image to each other. So we'll stop our discussion here on photochemistry, and then we'll discuss about a few reactions which are photochemically, which occur in nature photochemically, and those there are many examples of photochemical reactions, like say photosynthesis or vision, like the way you are watching me, like light is falling on your eye, and there is a interesting photochemistry. There is a protein called retinal, and then it's a rhodopsin protein, and the protein name is rhodopsin, and there is a chromophore which is known as retinal, and there's a double bond. There are many double bonds inside this chromophore, and then around a particular double bond there is a cis trans isomerization happens, and after absorption of the photon, and this cis trans isomerization leads to a structural change of the chromophore. And then the protein also makes a change. The protein actually fold in a different way, and that actually opens up. These proteins actually sit in your cell membrane of your cell, and that actually opens up some ion channels in your membrane, and some protons actually come in and out. That creates a membrane potential difference, and that creates a stimuli or the electrical impulse, and that actually propagates through the nerve cells. And then your brain registers the signal, and it says, okay, so fine, I have seen a photon. Now you see a photon, and you see a photon of different colors, and then actually you construct an image what you were seeing, and that's how it works. So everything behind vision is nothing but very fundamental photochemistry and some subsequent downstream biological reactions or biological response. Similarly, photosynthesis was one of the things where actually the light energy is absorbed by chlorophylls and subsequently transferred to a reaction center where you have a charge separation, and then you oxidize water to oxygen, and as a byproduct to get oxygen, and you reduce some coenzymes, and those coenzymes further reduce actually carbon dioxide to make food. So again, photosynthesis, the first part, the light harvesting part, is nothing but very interesting photochemistry. But we'll be talking about not photosynthesis or the vision chemistry. We'll be talking about the photochemistry of the atmosphere, like what happens when the atmospheric molecules absorb light, and what are their interesting rates, what are the photochemical rate constants, and how basically we will be particularly talking about the ozone chemistry, how the ozone layer actually protects us from the harmful ultraviolet radiation. That we'll also be talking. So we'll be talking about two different things. One is combustion chemistry, and one is photochemical reactions, which is the environmental chemistry. Atmospheric chemistry we will call it. So that falls under the big subject which is known as photochemistry. So we'll be discussing it when in terms of the kinetics of those processes. Thank you.